So this is section 1.3 diode circuits and DC analysis and models. And the author first starts out by drawing the circuit symbol for a diode, where this is plus and this is minus, and this is your voltage across the diode. And then he shows you, like, this is what if you actually bought one. It would look sort of a cylinder and with a stripey right here. And just when you're building a circuit yourself, this stripe here matches this stripe here, or that vertical line there matches that vertical line. So this is your P part, this is your N, this is plus and minus for a forward bias diode. And just something that I looked up too was we talked about it previously, the variactor diode, which was used to make tuned circuits, has this symbol here, and so I guess this is sort of shows that you can tune it via that capacitance. And so a diode is a two-terminal device right here, because this is representing the real one right here. We have two terminals, and it is nonlinear. It is a nonlinear device, or you could say it has nonlinear current voltage characteristics. Okay, remember that formula for the diode current. It was ID equals the reverse saturation current over VD over VT. So that's the thermal voltage minus 1. And so this is a nonlinear equation. For a resistor, you have V equals IR, which is linear. So you can say V is equal to, or I mean I is equal to V over R. So it's linear relationship between I and R. And then they give the one of the common uses for a diode is to make a rectifier circuit. And so we have some AC voltage source. I'll kind of denote it looking like this. And so we'll call this V input. And then we have a diode. And then a resistor. And we'll take the output of the circuit across the resistor. So we'll call this V out, plus, minus. And if our input signal looked like this, so this is voltage over time. If our input look, is a typical sinusoid, then our output V out would look like this. Where this, again, this is voltage and this is time. And so every time it's positive, you get a positive, and then it's reversed, and so now we're in reverse bias, and so you get nothing, no current, and then positive, and then reverse bias, then positive. So this is where it's forwarded bias, reverse bias, forwarded bias, reverse biased. So that's a rectifier signal. The circuit is said to rectify the input signal. The next section is 1.3.1, and this is interactive and graphical analysis techniques. And so we have this circuit, and so I'm drawing the power supply, and we have a resistor, and we have a diode. And I'll represent ground like this. And we have VD across the diode. And then this is going to be V power supply. And so this is plus, this is minus. So if we do KVL around this loop here going in this direction. We got minus V power supply plus, and we'll just call the current here ID. So we'll have ID R, and then plus VD equals 0. So that's just KVL. And you could rewrite this as V power supply equals IDR plus VD, the voltage across the diode. And we could also solve this for ID. Is this going to be equal to the power supply voltage minus VD over R, which is the same thing as V power supply over R minus VD over R. And so we're going to use this equation here for our interactive, solving the circuit by interactive or iteration. And we'll use this equation for the graphical analysis. I wrote this wrong. This shouldn't be interactive. It should be iterative. Iterative, not interactive. And same thing here. This should be iterative. Okay. So iterative just means trial and error. And the last thing that we need in this puzzle is our diode equation. Remember, ID is equal to the reverse saturation current time over to the exponential of VD over VT, which is thermal voltage. And so knowing these three equations, we can solve whatever we need to do. So in example 1.8, okay, they tell you that V power supply is equal to 5 volts, so that's that power supply, and they tell you that the reverse saturation current is 10 to the minus 13, and we're going to go e to the VD over 0.026 minus 1, so that's our ID, all of that, times R, which they told you was 2,000 ohms, plus VD, okay? And so all you're going to do now to solve this iteratively is to start out with some value of VD, and you're just going to guess a value. You could pick anything you want, you know, and then you'll basically solve it, and does it equal 5? If it doesn't, then you'll pick another value, higher or lower, until finally you pick a VD. When you evaluate this whole equation, it equals 5, and then you're done. So that's the iterative, the trial and error way to do it. And so in that example, if you eventually pick a VD of 0.619, then this side will come out to be 5. So that's the trial and error method. And the graphical way is to use this equation. We'll say new line, our new thing. And so that equation, I'll rewrite it again, was ID equals V power supply over R minus VD over R. And then we have our other equation, which was the ID equals IS times e to the vd over vt minus 1. And so you're just going to plot these two equations. Plot, and where they cross is the solution, okay, to the problem. So if I have an VD and this is ID, and how you plot this equation, they tell you in the book, is first assume that ID, so first assume ID is equal to 0, and so that leaves us with VPS over R is equal to VD over R. So I'm just using this equation here, the first one, and saying ID equals 0, and then the R's cancel out, so you're left with VPS equals VD, or VD equals VPS. So you just put a little dot right here. This is I equals 0, and this is VPS. And then assume, the next start is assume your other variable, VD, is equal to 0. Now if we assume VD is equal to 0, we get ID is equal to VPS over R. Again, that's just the first equation, setting the second term here to 0. And so if VD is equal to 0, that's on this vertical axis, and we'll say VPS over R. Okay, and then you can just connect the lines together. And they call this line the load line. So this is the load line is sort of the constraint that the circuit is putting on the element. And then we just plot this equation out using what we know, and you get some, diode thing. And so where they cross is your solution, which they give you is a VD of 0.619 volts and 2.19 milliamps. And so that's where they cross, and they call that the Q point. I think a better name would have called it the O point, but basically it's the operational point. So that's where the circuit and the elements all operate at. Okay, so they call that the Q point or quiescence point. And for our given circuit and conditions of resistor and power supply, that's the point where that the current and voltage intersect. So that's the iterative and the graphical way to solve the diode circuits. The next section, 1.3.2, talks about the piecewise linear model. And so you approximate the diodes, say IV curves, using linear relationships. And remember, it's not really linear because we had that ID equals IS and VD over VT minus 1. So it's not linear, but we're going to approximate it. And so we have our curve here, and we have VD and ID here, and a diode that's forward biased looks like that. And so we're just going to basically take a line right here. And the line is going to have a slope equal to 1 over RF. And so this is the forward, they call it forward diode resistance. Okay? And it's for VD greater than V, was that gamma? Or the turn, and they call this the turn on or cut in voltage. And so our diode now will look something like this, where this is plus, this is minus. We have our resistor that we're using, and then we'll put in a little power supply here, and we'll call this V gamma for our turn-in voltage. And so that's our model for this, basically. I shouldn't say equivalent. It's it's approximately equal to this over here. This is P. This is N. And so this is when the diode is on, and when the diode is off, our model becomes this. Plus, minus, and this is VD. Oops, forgot that, VD. And so it's basically just a open circuit. So that's our piecewise linear model for a diode. And now we're going to work another example. Example 1.9, where they want you to solve the circuit using the piecewise linear model. And so it's this circuit that we already did. This is plus, minus, this is V power supply, which is equal to 5 volts. We have our resistor, R, and which was equal to 2,000 ohms. And then we have our diode, plus, minus, VD. And we are told that RF, that's the forward bias or forward diode resistance, is equal to 10 ohms. And we're told that the turn on or cut in voltage is equal to 0.6 volts. And what they want you to figure out is what is ID and what is the power of the diode. So power for the diode. Okay, so we're going to change it to our piecewise linear model. We got R, and then I'm just going to draw it so it's more obvious. So we have our resistor, we have our power, our voltage, and so we'll go plus, minus, this is VD, and this was 2,000, and they told us this was 10 ohms, and this was 0.6 volts, okay? And this was 5 volts. And we want to know what ID is for this. And so you just do KVL at this point. Minus 5 equals ID 2000 plus ID 10 plus 0.6 is equal to 0. Whoops, minus 5 plus. So there's the power supply. Yep, that's right. So this is KVL, Kirchhoff's voltage law. And then you just solve for ID, which is going to be, what is that? 4.4 divided by 2010. ID equals 4.4 divided by 2010, which is equal to 2.19 milliamps, which is the same thing as that we got before in the previous examples. Then power, is I times V, and so we know what I is. That's 2.19 milliamps, and the V is going to be VD, so that's going to be the 2.19 milliamps times 10 plus 0.6. So that's the voltage drop across this resistor plus the voltage, the 0.6 volts is going to equal the VD out there. And so we get power is equal to 1.36 milliwatts. So that concludes this section of the book.